Hello everyone, welcome to this class of applied optics. Today we will learn more about geometrical optics. In previous class we talked basics of geometrical optics. We learned about what is K, which is your wave vector, and then we learn about frequency, the definition of frequency, the definition of time period, and then we learn about angular frequency of a wave, and then we saw how to represent a wave function in complex representation. Today we will learn ray theory. In this module 1, today we will learn ray theory and Fermat principle. These parts are already covered. The introduction of geometrical optics we have done in the previous class, and in module 1 we will today learn about ray theory and Fermat's principle. Now, as discussed before, the different regimes of optics are geometrical optics, wave optics and quantum optics. In geometrical optics, we assume that wavelength, the extent of wavelength is almost 0. We neglect the finiteness of the wavelength, and this geometrical optics will talk about the part of the optics where diffraction is neglected. To understand what diffraction is, you can consider a sheet with an opening, with an aperture, and then you shine a parallel beam of light on this sheet. Then here on the screen you will see that due to this opening you will see a bright spot in this region. Okay. Now, if you start reducing the size of this opening, then what will happen is that this bright spot will extend in the shadow region here. Okay. The extension of this bright spot in the shadow region is what we call diffraction, and this phenomena is neglected in geometrical optics. We do not consider diffraction here, and we will consider the light as a ray, and wavelength is neglected, the finiteness of the wavelength is neglected. Okay, and therefore, the geometrical optics is defined as the field of optics where finiteness of the wavelength is neglected. And this regime of optics can be studied using Fermat principle. Okay, in next slide we will learn what a Fermat principle and how does it governs the geometrical optics. Now, according to this principle, the ray will correspond to that path for which the time taken is an extremum in comparison to nearby paths. What it says is that suppose we have 2 points A and B given in space. A ray which starts from point A may travel to point B following infinite many paths. Suppose one of the path is given by C. Suppose this path which is given by a curve C represents one of these paths. Another path is represented by this dashed line, and which we name as curve C prime. C prime represents the dashed path, and continuous line is represented by curve C. Now, let us assume that in this path AB on curve C there is a infinitesimally small part of the curve which we call as ds. Okay. Now, let us calculate the time which a ray takes in traversing this infinitesimally small curve which is ds. Now, this time can be calculated once we know the speed and refractive index of the medium in which the ray is travelling. let us assume the refractive index of the medium is n. Okay, then the speed of the ray in this medium would be c by n, which is written here. Okay, and therefore, if you want to calculate the time spent by the ray in traveling the length element ds, then this can be given by this relation, and which is ds by c by n, where d tau represents the elemental time which the ray takes in covering distance ds. This relation can be written as n into ds by c. Okay, where n is a refractive index of the medium and c is the speed of the light in vacuum. Now, once we know the time which a ray takes in traversing distance ds, then we can also calculate the time the ray takes in traversing the whole curve path c. Okay, and now the whole time can be calculated by assuming several such small length element along curve c. Okay. Now, suppose there are very large number of these length elements, and then we can calculate the time for each of these length element, and then we can sum them up. Now, once you sum them up, this will give you the total time the ray will take in traversing path c. This total time would be given by tau, and which would be equal to 1 by c sigma over n I ds I, where ds I is the path length element for a strip I, where I is any random strip, and ds I is the associated path length, and n I is the refractive index of that the medium within that strip. Okay, I repeat, we choose a random strip, a random part, a random length element along the curve C. In this random length element, the length of this curve is dsi. The refractive index of the medium within this length element is ni, and we call this element, or we name this element as ith element. Now, to calculate the total time, we will have to sum over all these I elements, all the elements. Therefore, we are summing over n I ds I. Okay, and I runs over the number of elements, total number of elements. If the number of elements are very huge, then we can replace this summation with an integration. Okay, where this integrations runs from point A to point B along this curve C. Okay, and this dsi would then be replaced by ds, and I would be replaced by n, and the summation is, as I said, is replaced by integration. Okay, and this is how we can calculate the total time which a light ray takes in covering the whole distance from A to B along the curve C. Okay, now in this formula, n ds is the optical path length, ds is the distance, n is the refractive index. If you multiply n with ds, it will give you optical path length. Okay. Now, as I said, if a ray start from point A and goes to point B, it may take many paths, and the question is, the fundamental question is, which path the ray will prefer. And as per the Fermat principle, the ray will prefer the path for which the time taken is extremum. What does extremum mean? Extremum means extremum means either maximum or minimum or stationary. Okay. Now, we have this integration. Okay. C is a constant, therefore, we are removing it from our further calculation. We are just interested in optical path length, and the question is which path the ray should follow. Fermat principle says it will follow a path for which the time is extremum. Okay. Now, here if this particular path is extremum, if the C is extremum and next to C path there is another path which is C prime, which is slightly varied from C and which is not extremum, then any variation from path C will give you 0 here. The variation path C should be 0 as per the Fermat principle. Okay. And if for a given path this variance is 0, that particular path would be chosen by the ray, and this is what Fermat said. Now, as an application of this Fermat principle, or we can say that we will understand the reflection and refraction under the light of these this Fermat principle. To understand the phenomena of reflection, let us first consider a mirror which is designated by Mn, a line Mn, and this dark line is our mirror. A ray starts from point A and then it falls on the mirror, and then after falling on this mirror it goes to another point B. Point A is the start point and point B is finishing point. Now, there are multiple paths the ray may follow. The one path is A, P, B. Other alternative path may be A, Q, B. Again the same question, which path the ray should follow. Now, to understand this, we will again resort to Fermat principle. Okay. But to really understand what exactly is happening here and how to decide whether a particular path is extremum or not, let us assume a point A prime on the other side of line Mn, and this distance is equal to this upper distance. What I mean to say is that the distance AR is equal to the distance A prime R. Okay. Now, if A prime is mirror image of A, then the rays which are starting from point A will also appear at to start from point A prime, and these are the two possible rays which we discussed. These are the two possible paths which we discussed. Okay. And of course, the shortest path would be the path for which this line is a straight line, and therefore, A prime A, A prime P B, which is a straight line, would be the shortest path which is an extremum, and therefore, it follows the Fermat principle, it satisfies the Fermat principle, and this path would be the extremum path, and this is the path which the ray will follow. And another important point is that if you want to prove this fact geometrically, then what you have to do is that we will calculate the optical path length. Now, how to calculate the optical path length in this case? the optical path length is the length of the path which the ray is following. Now, here in this figure the ray is starting from point A, it is going to point B say, and then it is reaching to the final point, the destination point B. For a while assume that the ray falls on the mirror at point B, although there is a equal probability that it may fall on point Q, but for starting our calculation we assume that the ray path is APB, and we will check whether this ray path is extremum or not. Okay, the optical path length is here, the path length A, P and B. How to know whether APB is extremum or not? Let us see. APB is equal to AP plus PB. Okay, here what is AP? In this triangle, AP is hypotenuse, and therefore AP would be square root of AR square plus PR square. Similarly, PB in this triangle can be expressed as square root of suppose this is point C. Yeah, let us see what is written in the previous slide. Okay, no name. Okay, this suppose this point is C, then it is equal to BC square plus PC square. Okay. Now, what is AR square and PR square? AR square is equal, AR is equal to H, therefore AR square would be H square, and PR is X, therefore PR square would be equal to X square. Similarly, here BC is again equal to H. Okay. And the point to be noted is that we have assumed that A and B are at the same height from the line MN, as is clear from the picture, and PC is equal to L minus X. And what is L? L is the horizontal distance between the points A and B, as shown in this picture here, and this is our optical path length OPL. Now, once optical path length is known, Fermat said it would be optimum, or it would be the optical path should be extremum. How to check whether it is extremum or not? Let us differentiate it. We will take derivative with respect to the independent variable. And what is the independent variable in our case? We can see here in this picture, the point P is the point on the mirror MN where the ray from A is falling. Okay, and the ray may take several paths. It may fall at this point and then go to point B. It may fall at point P and then go to point B. It may fall on point Q and then go to point B. Therefore, the variable quantity is X, which is the horizontal distance from A to the point where the ray falls on the screen, the perpendicular to the points where the ray falls on the screen. PS is the perpendicular where the ray falls on mirror P, and X is the horizontal distance between point A and S. Okay, it tells about the horizontal separation between point A and perpendicular to the point of incidence of ray on mirror MN. Okay, therefore, X is the variable here. Okay. Therefore, to check whether this path is extremum or not, we will have to differentiate it with respect to X. We will differentiate this optical path length with respect to X to check whether it is optimum or not, and if it is optimum, then this derivative must be equal to 0. Okay, let us do this and see what do we get. Then from here we will get 1 by twice of H square plus X square, and in the numerator we will get twice of X here, and here in the denominator again we will get H square and here L minus x square and minus twice of L minus x into minus 1. This is what we get. This would be equal to 0. Okay. Now, if you see in the figure it and check what is theta 1, then you can see that theta 1, or let us calculate sin theta 1. Sin theta 1 is equal to x by square root of h square plus x square, and sin theta 2 is equal to h square plus L minus x whole square, and in the numerator for theta 2 this is the hypotenuse, and hypotenuse is equal to h square plus L square, and this perpendicular is L minus x. Okay, this is how sin theta 1 and sin theta 2 are defined in the figure. Now, we will see that we will substitute sin theta 1 and sin theta 2 in this expression, and from here what do we see is that this is equal to, first term is equal to sin theta 1 and second term is sin theta 2, which gives theta 1 is equal to theta 2, which is exactly the law of reflection. In reflection, the angle of incidence, which is theta 1, must be equal to the angle of reflection. Theta 1, which is angle of incidence here in this figure, this must be equal to the angle of reflection, and this is what we got using Fermat principle. It means the ray path, if a ray starts from point A and lands up on certain point on mirror B, and ultimately it get collected at point B, okay, and then from this figure you can say, or from this calculation you can say the ray will follow a path for which P is situated in such a way that angle of incidence is equal to angle of reflection. Now, once we studied reflection using Fermat principle, now we should study the second important law, which is law of refraction. Okay. To study the law of refraction, as you know, we require two media. Okay. Now, we again draw a line, horizontal line, which we name as PQ, and this thick horizontal line PQ is an interface between the two media of refractive index N1 and N2 respectively. Okay, refractive index, the medium of refractive index N1 lies above the interface PQ, and the medium of refractive index N2 lies below the line PQ. Now, the source or the ray start from point A, which is situated at a distance h1 or at height h1 from line PQ, and then it passes through this interface PQ, and then it is getting observed at point B, which is at depth h2 from line PQ. Now, the ray which is starting from point A and ultimately reaching at point B, it may take infinite many paths. Which path would be the extremum? Which path the ray would follow? Okay. Now, for minimum optical path, the incident ray, refracted ray, and the normal to the interface. This line defines the normal to the interface. Okay, they all must lie in the same plane. This is what Snell's law said. Okay, we will do some geometrical calculation as we did in the previous case, and then we will see what Fermat principle gives us in this case, in this refraction case. Okay. Now, here we assume that the ray which is starting from point A falls at point R on interface PQ, and this point R is x distance away from line AM, and the point A and the horizontal separation between point A and point B is capital L. Under this situation, let us calculate what AR is. AR is this distance. Now, AR would be equal to square root of x square plus h1 square. Similarly, we can calculate BR, which is this distance. BR would be square root of L minus x square plus h2 square. Once these two distances are known, we can calculate sine of theta 1 and sine of theta 2, where theta 1 and theta 2 are angle of incidence and angle of refraction respectively. Okay. Once theta 1 and theta 2 are known, then we can move forward for calculating the optical path length, as we did in the last slide. Now, how to calculate the optical path length? The optical path length, as visible in this figure, would be AR plus RB. Okay. If you add them up, you will get optical path length, but in this particular case, the upper medium and the lower medium are different, and they have refractive index, which is refractive indices which are different from that of air, and therefore, in addition to AR plus RB, we will have to multiply AR with N1 and RB with N2, which are their respective refractive indices. Okay. N1 is the refractive index in the upper medium, N2 is the refractive index in the lower medium. Therefore, the effective optical path length in the upper medium would be N1 into AR, and the effective path length in the lower medium would be N2 into RB, and this is what exactly we did. We calculated the optical path length in the upper medium and then optical path length in the lower medium, and then sum them up to calculate the total optical path length. Once total optical path length is calculated, we will substitute for AR and RB from the previous slide. Here we have already calculated, and this expression, this equation number 36 will now give us the expression for optical path length. Now, we will resort to Fermat principle, which says that if you take the time derivative, if you take the derivative of the optical path length with respect to the variable which is x here. Yeah, you can see in this figure x is the variable here, because the point R may vary depending if you vary the path which the ray takes, then the point R will vary, and therefore, x is the variable, and this is why we will differentiate the optical path length with respect to x, and as per the Fermat principle, this differentiation must be equal to 0, and once you do this, you will get equation number 37. Okay. And we have already calculated the expression for sin theta 1 and sin theta 2, and if you substitute for this and this quantity, then you will get this expression, and this is nothing but Snell's law. N1 sin theta 1 is equal to N2 sin theta 2, or sin theta 1 upon sin theta 2 is equal to N2 by N1. It means that the ray will follow a path for which this relation holds. Yeah, and therefore, it is again established that Fermat principle is capable of deciding the path of the ray. Now, suppose instead of having only two media, we have a huge number of layered media. Okay, suppose we have N1, N2, N3, N4, N5, N2 is here, N3 is here, N4 is here, and so on. Then this same Snell's law can be written as N1 sin theta 1 is equal to N2 sin theta 2 is equal to Ni sin theta I and so on and so forth. Okay. This is a generalized form. Okay. Therefore, we may say that Ni sin theta I is a constant if you keep varying the refractive index in a layered manner in one direction only, then Ni sin theta I would be constant. And what type of constant is that? It is invariant. Yeah, it is invariant of ray path. Okay. Now, once it is done, we will now see this, what is the application of this ray invariant quantity. Okay. Now, suppose as we discussed in the previous slide, we have layered media of different refractive index. Okay. The the lowermost medium has refractive index N1, and then upper one has refractive index N2, a bit upper one has refractive index N3, N4, N5 and so on. And refractive index is varying only in vertical upward direction. Okay. Under this particular case, we can derive a ray equation which will tell the curve which our ray will follow. How to derive this? Now, here as I said before, N1, N2, N3 and N4 are the refractive indices of different layer medium, and this is the ray which will follow a particular path following a Snell's law, or we can derive such a equation for the ray path if the thickness of these medium, this layered mediums are very small. Okay, and if these thicknesses are very small, then instead of having this discrete ray path, we can rather draw a continuous curve which represents the ray path. Now, suppose in vertical direction we have x axis, and in the horizontal direction we have z axis. Then a small element of ray path may be represented by ds, and it will be slanted at angle theta with respect to the horizontal direction. Okay, and we may say that along horizontal direction, the horizontal component would be dz and the vertical component would be dx of this length element ds. Okay. Now, we define now a quantity which is n x cos theta x, and this quantity would be ray variant. As discussed before, how can this quantity be a ray invariant? Now, if we launch a ray and then we draw a perpendicular at each interface, then this angle would be the angle of incidence and this angle would be the angle of refraction. In this medium, the second one, this angle would be the angle of incidence and this angle would be the angle of refraction. Now, suppose this is phi 1, this is phi 2, this is again phi 2 and this is phi 3 and so on. Then Ni sin phi I would be invariant. Okay. Ni sin I phi, as discussed in this previous slide, it would be constant, it would not vary. Okay. Now, if we write this invariant, which we call ray invariant in terms of cosine, then it would be written in the following form: Ni cos theta I. What is theta? Theta is this angle. This is theta 1, this is theta 2 and so on, the other side of phi. Phi plus theta is equal to 90 degree. Okay. Then this would be your invariant. Okay. And if this refractive index variation is only in one direction, as I said before, and the thickness of different layers are very small, then instead of writing this invariant quantity in discrete form, we can write it as a continuous variable. Therefore, we may write it as n function of x and cos theta, where theta is a function of x. Okay. There is a very slow variation in the refractive index along x direction. okay, and then we define a quantity which is beta tilde, which says that this nx cos theta x is ray variant, this is the invariant of ray path. Once this is defined, then we can calculate the path length, the infinitely small path length along this ray path, and this is using this diagram we can say that ds square would be equal to dx square plus dz square. Okay. After a little bit of mathematics we will get this relation, and from the figure we can see that cos theta would be equal to dz by ds. Okay. Once and we know that cos theta is also related to beta tilde, which is ray invariant. Therefore, cos theta may equivalently be written as beta tilde upon n function of x. Okay. Now, using this, equation 39 may be written as dx by dz whole square is equal to n square by beta tilde minus 1. This is ray equation. Now, this ray equation, which is represented by equation number 40, may equivalently be written in different form. How to write it in different form? Just differentiate equation 40 with respect to z once more. Then we will get this relation, and after a little bit of simplification, we will again get a modified form of this ray equation. Equation number 40 and 42, they both are called ray equation, and they trace the ray path. Okay. Now, we will take an example on this topic. Now, suppose we have a homogeneous medium, and for which refractive index, which is a function of x, would be constant, because in homogeneous medium refractive index does not vary. Then how to decide the ray path? To decide ray path, we will start with this ray equation. Okay. Now, since n is independent of x, therefore, this term would be 0, and therefore, right hand side of the ray equation would be 0. This is what we are now left with. After substituting n is equal to 0, we will get d square x upon dz square is equal to 0. Now, if you solve this equation, how to solve this? Integrate it twice, then ultimately you will get a equation which is x is equal to az plus b, where capital A and capital B are constants, and this is a equation of a straight line, which says that in homogeneous medium the ray would follow a straight line, which is quite obvious. This is what we observe in our daily life. Okay. If light a torch, then the ray which is emanating from the torch will go in a straight line. Okay. It means that things are correct here. Okay. Now, this is all for today. I end my lecture here with a ray equation. Thank you for your patience.